Hello again, welcome to Hi-Hats Devlog number 2. My name is Carter Anderson, and today we're going to be covering Hi-Hats online multiplayer implementation. This video is going to be an introduction to Hi-Hats multiplayer implementation, but I hope it's also a good introduction to how you would tackle programming an online multiplayer game in general. What you're seeing here is 3 clients running on the same machine as the server, but they're simulating packet loss and latency, so the connection should be approximately the same as it would be in the real world. It's not 100% perfect yet. There are some sources of desync and some things that we just don't sync at all. For example, projectiles are just completely ignored. But in general, it is actually playable. Your first step when starting an online multiplayer game should be selecting a network model. You have to answer questions like, who is the authority, who can I trust, how much does this need to scale, etc. In general, you don't want to trust the client. For example, if you're writing an FPS and you let people determine when their shots hit, then somebody could send you a malicious packet that says, I hit this person 10 times, but they never hit anybody. In the case of Hi-Hat, it doesn't need to scale that much. We only need to support single rooms with a few players in a given instance, and we definitely don't want to trust the clients for anything but their inputs. So a server-side authority is probably the way to go. There are mixed models and more scalable models where you have multiple servers that the clients are talking to, but in this case, we can keep it simple. The client will send inputs to the server will process those inputs in some way, and then it will send the results back to the clients. And now we're going to talk about the foundation of networked multiplayer games, loot boxes. Just kidding. In all seriousness, the foundation is time synchronization. When an event happens where multiple computers are involved, it's generally important that they agree when it happens. In our case, we consider the server's time the true time. The trick is to get client synced up with the server's time. Typically, the following algorithm is used. The client makes note of its current time, C0. It then pings the server. The server responds with its current time, S. The client then receives the server's time and makes note of the time of receipt, which we will call C1. We can then calculate the round trip time, which is the time it takes for the client to make a request and then receive a response, using C1 minus C0. In a world without latency, we could just take the server time S and subtract the client's initial time C0, and that would give us the delta, which we could then add to future client times to estimate the current server time. Unfortunately, we live in a world with latency, so we must account for that. Fortunately, we recorded the round trip time, half of which is a pretty good estimate of the delay between the client and the server. So once again, we take the server time S, subtract the initial client time C0, and then also subtract the round trip time divided by 2. For a more accurate estimate, we can repeat the process multiple times and average the results. So, we can estimate the server's time using the current client time. What do we do next? As we play the game, the server is going to send us information about the current state of the game. This will be info like game object positions, velocities, as well as events like attacks and picking up hats. Each of these states will have a server timestamp, and we need to decide how to order and render those states. I find it easiest to think about this problem as a timeline. Let's consider the case of a player's position. Pretend the current server time, as estimated by the client, is 600, measured in milliseconds since the game started. Let's say the server sent us 2 position packets, one with the timestamp 100 milliseconds, and the other at 500 milliseconds. We could just render the last state we received from the server. This is as close to real time as we can get, but it looks choppy and it's hard to follow when you're actually playing the game. We can do better. If we interpolate between states, we can get nice, smooth movement. But we do have a problem. The states we receive are always in the past, because the server takes time to send them to us. To solve this, we can offset the client's estimate of the current server time during playback to increase our likelihood of having states to interpolate between. This offset should be some function of past latencies between the client and the server. In Hi-Hat, I just use the mean of the round trip time. This number is unstable, so to keep the playback smooth, I interpolate the last offset to the current calculated offset. For now, let's just pretend the current offset is 100 milliseconds. As you can see, playback is now nice and smooth. In Hi-Hat, I use different functions for different state types. I use a binary flip for things like booleans or events that need to be triggered once. I use linear interpolation for pretty much everything for a nice smooth interpolation, unless that thing has a position and a velocity, in which case I use Hermite splines. This takes velocity into account during the interpolation and gives us a nice smooth curve. The timeline code is generic, so it can be used in pretty much all cases. This gives us consistent timing for all states and events. But even with the delayed timeline implementation, sometimes the playback gets ahead of the last server state. To illustrate this, I will force the server to stop sending position updates. As you can see, when the client got ahead of the last server state, the simulation froze. To combat this, we can use our knowledge of past state to extrapolate future states. Godot makes rigid body extrapolation easy. The client and the server are running the same code, so we can just set the client to the last known good position and velocity and let it run. Extrapolation greatly improves the experience on unstable connections, but there are some caveats to be aware of. Eventually, the client and server states will diverge, so it's important to limit the duration of the extrapolation to avoid feeding the players bad information. Also, some states, such as player movement, are discontinuous and unpredictable, so extrapolation should be used sparingly, if at all. With the features we've covered, changes on the server are now smoothly rendered on the client. But we still have one problem to solve: player movement. The world is a dark place full of dirty cheaters. We can't trust them to tell us where they are or what they're doing. We want the server to validate all player inputs before we render them. So naively, as a local player, we could just send our inputs to the server, wait for the results to come back, and then render those. But, as you can see here, games played over the internet have lots of lag, and that lag is noticeable. The solution to this problem is called ClientSide Prediction, and it boils down to this. Clients can't trust other clients to be upstanding citizens, but they can trust themselves. Just like extrapolation, we can exploit the fact that the client and the server can run the same code. As soon as a client has player input, it can immediately run the movement code, then send the input to the server to process. This gives the local players immediate feedback, and it makes the game feel a bit more normal. If our movement code is deterministic, we can stop here. The server will process the input and send all of the clients the final state, which will match our local state. In hi-hat, movement is not deterministic due to interactions with other players, friction, and other forces. So we need to both process inputs locally and account for discrepancies as they come from the server. To do this, we take the last state we received from the server, which we trust. We set the local player to that state, and then we replay all inputs that occurred after that state. The result is pretty good, but there is still some jumping around as new server states come in and correct local errors. To make this a bit smoother, we process the inputs immediately, ignoring server states entirely, but then we interpolate to the server state with inputs replayed on top of them. If you're confused, don't worry too much. It's a lot to process. I was in the same boat when I was learning this stuff. When I was implementing this feature, I created debug visualizations that I think help solidify the concepts. The blue ball is the last position received from the server, and the red ball is the server position with local inputs replayed on top. The player is rendered at the fully local movement, but it's interpolated to the red ball's position, which is the result of our client-side prediction. This is currently running on a pretty fast connection, so there aren't many errors to correct. The server position, which is represented by the red ball, is basically the same as the local position. So let's dial up the latency to show why this technique is valuable. Now, the blue ball representing the server state trails far behind, and it's a bit more unstable. And the red ball doesn't line up with the rendered player's position nearly as much as it used to. But the rendered position smoothly error corrects to the client-side predicted position at the red ball. And I think that's neat. So I created something called a network spawner, which spawns a scene on both the server and the client at the same position. It assigns a unique network ID, which is used to reference the scene when we're sending updates from the server to the client. I also created the debug view that you're looking at now to ensure everything is synced up. Each net ID is hashed to create a unique color. This lets you visually compare the server and the client state to ensure that everything matches. Here are some quick notes on how I compose messages in hi-hat. By default, Godot's RPC system is not statically type-safe. The message producer must know the exact function signature the message consumer expects and compose a list of arguments that matches that signature. This is why I use a C# library called MessagePack whenever I send a message over the wire. MessagePack is an efficient binary serializer that lets me define a type-safe class-based contract. This way, the producer and the consumer are guaranteed a compile time to be synced up when it comes to the number, type, and order of data being sent. It also lets me define my own data types, which would crash Godot if I were to try to do that without message pack. The message sender creates a new message pack message. That then gets serialized to a byte array, which is passed into Godot's RPC system. And then the message receiver takes that byte array and deserializes it to the expected message pack message. Godot's RPC system is fantastic, but it biases towards sending small, node-specific packets. These packets are indexed using the node path, which must be unique. If a client receives a packet for a node that doesn't exist, it drops that packet. This becomes problematic if you are quickly adding or removing networked nodes, and/or you are using an unordered channel when you are sending those packets. This is why, when possible, I batch updates at a higher level and use the custom node IDs I mentioned earlier in this video. That way I don't throw out data when a node doesn't exist yet. This has the added benefit of reducing bandwidth used. We send fewer UDP packets, so we have fewer UDP headers. We send fewer RPC packets, which means we send less RPC metadata. And because we're sending more data per packet, that has more compression potential in eNet, which is the underlying network library that Godot uses. And that concludes Hi-Hat's networking overview. Next on the agenda is some closed alpha testing. The game is still very much under construction, but I do want to get it in a limited number of people's hands in the relatively near future. If that sounds interesting to you, just give me a shout out on Twitter, and I'll add you to the pool of people who I will eventually reach out to.